people who selected the destination would probably never see the ship leave the solar system behind. They would watch the launch, follow the first years of acceleration, and grow old while the nearest star remained a point of light ahead. Their children might inherit the first major repairs. Their grandchildren could be born after Earth had become too distant for an ordinary conversation. By the time the vessel reached its chosen planet, the names engraved upon its oldest walls might belong to ancestors as remote as medieval kings are to us. The answer depends upon a number that sounds simple: the speed of the ship. At the velocity of humanity's present interstellar probes, the nearest star lies roughly 75,000 years away. A generation lasting 25 years would repeat around 3,000 times before arrival. A vessel traveling at 1% of the speed of light could complete the same journey in approximately 425 years, allowing 14 to 17 generations to live during the crossing. At 10% of light speed, the distance would shrink to little more than 40 years, perhaps long enough for children born after departure to reach the destination with their parents. Every proposed technology creates a different human story. Slow ships require civilizations capable of surviving longer than recorded history. Faster ships demand energies, materials, and shielding far beyond anything currently available. Suspended animation could reduce the number of conscious generations while asking machinery to preserve sleeping bodies for centuries. Radical life extension might allow the original crew to arrive, carrying minds shaped by a world that had aged far beyond them. The number of generations becomes a measure of propulsion, biology, society, and the amount of human change a mission can endure before reaching another sun. The nearest star to the Sun is Proxima Centauri, roughly 4.25 light-years away. The number appears almost modest beside the dimensions of the Milky Way. Light crosses the distance in a little more than 4 years. A spacecraft must cover around 40 trillion kilometers, then slow sufficiently to enter the destination system rather than passing through it at enormous speed. A light-year hides distance inside a familiar unit of time. Light travels nearly 10 trillion kilometers during 1 year. Multiplying that distance by 4 creates a gulf beyond every journey completed by human beings. The farthest spacecraft have spent decades moving outward and remain less than 1 light day from Earth. Proxima stands more than 1,500 times farther away than a single light day. The distance would be larger if the mission selected another destination. Barnard's star lies around 6 light-years away. Tau Ceti is close to 12. The TRAPPIST-1 system, known for 7 rocky planets, stands approximately 40 light-years from Earth. Each additional light-year adds decades, centuries, or millennia according to the ship's speed. A destination selected for promising planets may require many more generations than a journey toward the nearest available star. The first interstellar mission would therefore face a difficult choice. The closest star reduces the voyage, though its planets may offer poor conditions for settlement. A more distant system could appear safer or richer while multiplying the time spent between stars. The ancestors choosing the planet would also be choosing how many generations must live and die before anyone reaches it. Voyager 1 provides the clearest comparison with technology humanity has already launched. It moves away from the Sun at roughly 17 kilometers per second. That speed can cross an ocean in minutes and travel around Earth in less than an hour. Applied to the distance separating stars, it becomes almost motionless. At a constant velocity similar to Voyager's, the journey to Proxima Centauri would last around 75,000 years. A generation of 25 years would repeat almost 3,000 times. A 30-year interval between generations would still produce about 2,500 generations. The original passengers would belong to a period farther from the arrivals than the earliest human cities are from the present. The ship could not rely upon any cultural institution surviving unchanged across such a duration. Every language spoken at launch would transform. Religions would divide and develop. Systems of government would rise, fail, and be replaced. The vessel's population might evolve biologically. Its inhabitants could forget Earth, rediscover it through archives, and reinterpret the mission repeatedly before completing a small fraction of the distance. Mechanical survival would become even less plausible. Voyager was built to operate for years and has endured for decades through exceptional engineering. A crewed vessel traveling for 75,000 years would need to replace nearly every component many times. It would need to rebuild the factories that produce those components and preserve the knowledge required to rebuild the factories themselves. The fastest human-made object has moved far more quickly than Voyager. Parker Solar Probe reaches close to 200 kilometers per second during its nearest passages around the Sun, propelled largely by falling deep into the Sun's gravity. If a spacecraft could maintain a comparable speed directly toward Proxima Centauri, the journey would still last more than 6,000 years. That would correspond to roughly 200 to 250 generations. The crossing would exceed the time separating modern humanity from the first large cities. A person arriving at the destination could study the launch civilization as an ancient culture whose political conflicts, everyday language, and social assumptions required specialist interpretation. Parker's record velocity cannot simply be converted into interstellar cruising speed. The probe reaches it while following a solar orbit. A generation ship must accelerate its own mass toward another star and later lose that velocity. Parker weighs less than a small car. An inhabited vessel could contain thousands of people, shielding, water, farms, factories, engines, and enough material to maintain a civilization. The comparison still reveals the distance between speed records and interstellar travel. Increasing Voyager's velocity by more than 10 times reduces 3,000 generations to a few hundred. The voyage remains long enough for the ship to develop a history deeper than that of most existing nations. Chemical rockets would struggle to change this scale. They release energy stored in molecular bonds and accelerate by expelling hot gas. This method can lift spacecraft from planets, send probes throughout the solar system, and place immense structures into orbit. Its energy density remains too low for pushing an inhabited world toward a meaningful fraction of light speed. A rocket must accelerate its fuel along with the vessel. Additional propellant increases the initial mass, requiring more propellant to accelerate that increase. Staging allows empty tanks and engines to be discarded, yet a generation ship cannot abandon most of its structure during a voyage requiring centuries of life support. It also needs fuel or another mechanism for slowing at the destination. Chemical propulsion could begin the journey and provide local maneuvering. The principal acceleration would need to come from a denser energy source or an external system. Nuclear reactions, fusion, antimatter, laser beams, magnetic sails, and other approaches attempt to escape the limitations of chemical fuel. A mission launched with only refined versions of existing rockets would remain in the realm of thousands of generations. The ship could reach another star eventually, provided its civilization endured longer than any continuous human project. The propulsion technology would shift the central challenge away from travel and toward the creation of an almost immortal society. At 0.1% of light speed, the vessel would travel around 300 kilometers during every second. This is already faster than Parker Solar Probe's record and far beyond any sustainable interstellar cruise achieved by machinery. Proxima Centauri would remain approximately 4,250 years away. A 25-year generation would repeat around 170 times. A 30-year generation would produce more than 140 generations. The first inhabitants could become legendary figures before the ship reached even 1% of the route. Their decisions would survive through law, architecture, genetics, and the initial direction of travel, while their personal motivations faded. 4,000 years offers enough time for cultures on Earth to transform beyond recognition. Languages spoken during the construction of the Egyptian pyramids survive mainly through inscriptions and scholarship. Religions, empires, technologies, and populations have changed repeatedly across a comparable interval. A generation ship would compress a similar depth of history within one enclosed structure. This speed might become possible through advanced nuclear propulsion or other large-scale systems, though maintaining the vessel for 4 millennia would remain a civilizational challenge. The passengers would have enough time to rebuild the ship repeatedly, alter its social order, and question whether the destination chosen by their ancestors still deserved their loyalty. At 1% of light speed, the character of the mission changes. The ship would move at nearly 3,000 kilometers per second. Proxima Centauri would lie about 425 years away before acceleration and deceleration were included. A generation lasting 25 years would repeat around 17 times. A 30-year interval would produce about 14. 14 to 17 generations can still transform a society completely. A child born during the voyage could know grandparents whose own grandparents were born aboard, while the founders belonged to history. The distance from launch to arrival would resemble the interval separating the modern world from the early 17th century. The vessel's oldest institutions could survive through written constitutions, ceremonies, education, and continuous use. Their meanings would change as new conditions appeared. A rule created during departure might become irrelevant after the ship's population, technology, or ecosystem evolved. The society would need enough stability to preserve the mission and enough flexibility to remain healthy. A 1% vessel would also endure severe physical hazards. Interstellar gas and dust would strike the forward shielding at tremendous speed. A grain weighing a fraction of a gram could release destructive energy. Radiation exposure would accumulate. The engines would need to accelerate a massive habitat and later slow it within the target system. 17 generations represents a plausible human chain. It also requires a machine and society capable of remaining coherent across more than 4 centuries without repair, trade, or rescue from an external civilization. At 5% of light speed, Proxima Centauri would be approximately 85 years away during the cruising portion of the journey. 3 or 4 generations could overlap during the mission. Some original passengers might survive into old age near arrival if life expectancy increased and acceleration periods remained manageable. A child born shortly after departure could grow old aboard. Their children would spend adulthood maintaining a ship whose destination had become visibly brighter. Their grandchildren might become the first people trained primarily for planetary arrival rather than deep space survival. The voyage would connect launch and settlement through families who knew one another directly. This continuity would reduce certain cultural risks. The founders could teach shipborne adults personally. Earth memories would remain alive through much of the crossing. The original language and mission purpose would change gradually within a chain of direct relationships. The technical demands would rise sharply. 5% of light speed is around 15,000 kilometers per second. The kinetic energy of a large vessel would be immense. Shielding against interstellar particles would become difficult, and slowing at the destination would require an energy investment comparable with acceleration. An 85-year crossing sits near the boundary between a generation ship and an unusually long crewed mission. Several generations would still live aboard, although the ship would no longer need to maintain a civilization for centuries. It would need to support full human lifetimes and transfer responsibility from the founders to descendants who could see arrival within their own future. At 10% of light speed, the direct travel time to Proxima Centauri falls to roughly 42.5 years. The actual mission would take longer because the vessel must accelerate, navigate, and decelerate. The voyage could still fit within one extended human career. Adults departing in their 20s might arrive in old age. Children born during the early voyage could reach the planet as mature adults. The mission would include 2 generations in the demographic sense, although many people from the original population could survive the complete crossing. This scenario changes the moral structure of departure. The people selecting the destination would share the risk of arrival. They could no longer place every consequence upon descendants. Children born aboard would inherit the mission, while their parents remained present to answer for its design. 10% of light speed creates extraordinary hazards. At this velocity, a collision with dust becomes comparable to an explosion. Individual atoms strike the front of the ship as high-energy radiation. Navigation systems must identify or clear material far ahead. Shielding powerful enough to protect a city-sized habitat would increase the mass requiring acceleration. The journey could be completed within 2 generations, only after propulsion and protection technologies reach far beyond present engineering. Speed removes centuries from the social challenge and replaces them with immense physical difficulty. At 20% of light speed, a spacecraft could cross the distance to the nearest stellar system in a little over 21 years. This velocity appears in proposals for tiny laser-driven probes. A powerful array near Earth could focus light upon an extremely light sail, accelerating a miniature craft without requiring it to carry fuel for the initial push. A nanocraft and a generation ship occupy opposite ends of spacecraft design. The probe can weigh grams, carry compact instruments, and pass rapidly through the target system without slowing. The inhabited ship weighs thousands or millions of tons and must protect human lives. It requires space, water, equipment, factories, and a propulsion system capable of deceleration. The laser energy needed to accelerate a crewed vessel would be incomparably larger. The sail would need to survive immense forces and maintain precise alignment. Once the ship left the beam, it would require a method to slow. A second laser installation could exist at the destination only after another mission built it. If these problems were solved, the journey could occur within 1 biological generation. People departing as children or young adults would arrive before old age. Babies born aboard would see the planet their parents selected. The phrase generation ship would become technically inaccurate since no necessary succession of generations would be required for completion. The travel time alone never gives the complete number of generations. Acceleration and deceleration can add years or decades. A ship cannot instantly move from rest to 10% of light speed without destroying its passengers and structure. The acceleration must remain within tolerable limits and within the capacity of the engines. A low-thrust fusion vessel might accelerate gradually for years. It could spend part of the journey building speed, coast through the central section, then rotate and slow for arrival. The average velocity would remain below the peak. A quoted cruising speed can therefore make the mission appear shorter than the full trajectory. Continuous acceleration at a force comfortable for humans creates another possibility. The ship could accelerate for part of the journey and decelerate during the remainder, providing artificial gravity through thrust. Reaching high relativistic speeds would demand an energy supply beyond present capability, though the crew's experienced travel time could become much shorter. Mission planners would count generations using the complete duration from departure to safe arrival. A vessel capable of reaching 5% of light speed might average only 2 or 3% across the route. Its 85-year ideal crossing could extend past a century. A mission apparently requiring 3 generations could require 5 after engineering reality entered the calculation. The length of a generation also resists simple definition. Demographers may use an average interval between the birth of parents and their children, often somewhere around 25 to 30 years. A generation ship could alter that interval intentionally. If adults began having children at 20, a 425-year voyage would contain more than 20 reproductive generations. If parenthood occurred closer to 35, the same crossing might contain around 12. Longer lives could allow several age groups to overlap, preserving direct relationships across much of the ship's history. The mission might schedule births to maintain a balanced population. A large first generation could be followed by smaller cohorts. During a crisis, births might be delayed. After an accident, the ship could encourage a rapid increase. The number of genealogical generations would differ among families. Some children might be conceived using stored reproductive material from people who lived on Earth. Their genetic parent could belong to the founder era, while their social parents lived centuries later. The ordinary language of generations would become complicated when ancestry, upbringing, and historical time no longer aligned. A useful estimate can divide travel time by 25 or 30 years. The lived society would contain overlapping, uneven generations shaped by medicine, culture, and demographic planning. Life extension could reduce the number of generations required without changing the ship's speed. If humans remained healthy for 200 years, a 425-year crossing at 1% of light speed might involve 3 long-lived generations rather than 17 ordinary ones. Some founders could meet people who would participate in arrival. Longer lives would preserve knowledge and institutional memory. Engineers could supervise systems for a century. Scientists could follow experiments across decades. People who remembered Earth could influence the voyage far longer than under present lifespans. The demographic consequences would be complex. A population containing many healthy adults would need fewer births. Resources would remain occupied for longer periods. Political leaders could hold power across several conventional generations. Younger people might struggle to gain responsibility within institutions dominated by founders. Long life would also need to protect the brain, body, and reproductive health through radiation exposure and artificial conditions. Extending biological duration increases the time available for cancer, chronic disease, psychological fatigue, and accumulated cellular damage. A medicine capable of slowing aging would need to operate under the harshest environment humans had ever inhabited. Life extension could turn a generation ship into a vessel of long-lived travelers. It would not remove the need for children, social renewal, and institutions capable of adapting beyond the perspectives of the launch crew. Suspended animation offers another route around generations. The passengers could spend most of the voyage unconscious, with metabolism reduced and bodies preserved through cooling, medication, or more advanced biological techniques. Automated systems would guide the ship and awaken the crew near arrival. No existing method can preserve a human safely for decades or centuries. Cells continue suffering radiation and chemical damage. Muscles, bones, circulation, and the brain require protection. The suspension chambers, computers, power systems, and repair robots must operate while the people best able to respond remain asleep. A mission could wake rotating crews for maintenance. Small groups might live aboard for several years, return to suspension, and hand responsibility to another group. The ship would contain 1 biological generation spread across centuries of calendar time. Individuals could experience only a fraction of the total voyage. This approach creates unusual social relationships. A person might wake to meet a colleague last seen by their grandparents. Children could be born during one maintenance period and enter suspension before adulthood. The chronology of age would separate from the chronology of the vessel. Suspended animation would reduce food and psychological demands while increasing dependence upon machinery. A generation ship at least allows living people to repair systems continuously. A sleeping ship asks automation to preserve both vessel and population through a darkness containing nobody awake enough to understand a failure. Digital minds could alter the answer more radically. Human consciousness might someday be copied, emulated, or transferred into computational systems. A digital traveler could slow its subjective processing during the voyage, experience virtual life, or remain inactive until arrival. The ship would still need physical hardware, energy, shielding, and repair. Information can degrade when storage is damaged. Computers require replacement. A digital population may demand less mass than biological habitats, allowing greater speed and stronger shielding. Generations inside a virtual environment could occur at any chosen rate. Thousands of subjective years might pass during a century of physical travel. The population could evolve culturally far faster than the ship moved. Another system could slow consciousness until the complete crossing felt like a brief sleep. Whether these entities remained human would become a question of identity rather than propulsion. A copied mind could share memories with its biological original and become a separate person through new experience. Several versions could travel toward different stars. A vessel carrying digital humanity might reach another star without any biological generation being born during transit. It could later construct bodies, create settlements, or continue living within machines. The number of generations would depend upon software, choice, and the definition of a human life. For a biological generation ship, population size would matter as much as travel duration. A voyage lasting 14 generations might begin with thousands of people and maintain enough genetic variation through careful reproductive planning, A voyage lasting 3,000 generations would face an almost unlimited sequence of demographic accidents. Every generation can experience infertility, disease, conflict, unequal reproduction, and random loss. A stable average population does not guarantee stable ancestry. If a few families produce most children, genetic diversity narrows. Stored embryos and reproductive cells could introduce additional lineages from Earth. The archive would need to survive the complete crossing. A cryogenic failure during the 10th generation might leave 14 later generations with fewer options. A 75,000-year voyage would require genetic stores to remain usable across periods longer than the existence of many human species. A larger living population provides resilience. It also increases the ship's mass, resource consumption, and manufacturing requirements. Propulsion systems capable of accelerating a small colony may be unable to move a city. The number of generations therefore affects the minimum scale of the vessel. A 40-year mission can rely upon a trained crew. A 400-year mission needs a self-renewing population. A 75,000-year mission requires a civilization capable of becoming an evolving species inside a machine. The first generation would be unique because its members chose or accepted departure. They would remember Earth, understand the launch technology, and possess direct relationships with the institutions that built the ship. Their education would be oriented toward operation, emergency response, and the transfer of knowledge. Their children would become the first people whose entire lives belonged to the vessel. They would grow up hearing that the mission had a destination while knowing they had never consented to its selection. Their parents might expect gratitude, discipline, and continuation. The children could experience the voyage as an inheritance containing both opportunity and confinement. By the third generation, Earth might remain emotionally present through grandparents or recordings. The ship would already possess its own history of births, deaths, repairs, accidents, and political disputes. The destination would belong to a future experienced mainly through education. Around the 5th or 6th generation, launch could feel comparable with a distant historical era. The original technical language might require interpretation. Traditions formed aboard could carry greater emotional weight than customs preserved from Earth. 14 generations would be enough for the ship to become a homeland. 3,000 generations could make Earth and the destination equally mythical. Two planets placed at opposite ends of a journey whose original meaning had disappeared. Knowledge must cross every generation successfully. The founders could leave manuals, simulations, artificial intelligence, and vast archives. Later technicians would need to understand machinery altered by centuries of repair. Written instructions become less useful when components, materials, and manufacturing processes change. Apprenticeship would preserve practical knowledge. A senior engineer might recognize a failing bearing through vibration before sensors issued a warning. A farmer could see subtle crop stress that models overlooked. A physician would interpret unusual symptoms within a population adapted to the ship. Each skill requires enough practitioners to survive accidents and demographic fluctuations. One specialist cannot protect the vessel across a lifetime. Every essential profession needs teachers, students, equipment, and institutions that maintain standards. A 14-generation mission could preserve continuity through direct chains of mentors. A 3,000-generation mission would experience repeated losses and rediscoveries. Some advanced technologies could disappear because the population lost the ability to manufacture their components. Later societies might rebuild them from archives. The arrival generation could possess technology very different from that used at departure. The ship might begin as an advanced spacecraft and reach the destination as a structure maintained through simpler, more repairable systems developed during the journey. Machines also possess generations. Engines, pumps, computers, seals, lights, filters, and structural plates would be replaced repeatedly. A 400-year voyage exceeds the expected life of nearly every complex component. The vessel must manufacture parts and reconstruct its own industrial base. The first replacements could come from stored spares. Later generations would use recycled material and locally manufactured components. Each part depends upon tools, measurement systems, software, and purified materials. A factory failure could threaten the ability to repair life support. A ship lasting 75,000 years would be rebuilt so many times that almost no original material remained. Its identity would survive through continuity of structure and purpose, similar to a city whose buildings, citizens, and institutions change while its name persists. The number of human generations and mechanical generations would interact. A long-lived machine reduces the knowledge burden. A system requiring frequent intervention keeps expertise active while increasing labor. Components designed for repair may be heavier and less efficient than delicate high-performance equipment. The ideal generation ship would carry technologies capable of being understood and reproduced by the society aboard. Its survival would depend upon compatibility with human institutions across time, rather than the maximum performance available on launch day. A journey lasting a few generations could maintain one language through education and daily contact. A voyage lasting dozens would produce natural linguistic change. Pronunciation, vocabulary, grammar, and meaning evolve even when recordings preserve older forms. Technical communication would require standardization. Emergency instructions and maintenance procedures must remain clear. The ship could maintain an operational language taught formally while allowing ordinary speech to change. After hundreds of generations, the founder language might survive in ceremonies and archives like an ancient scholarly language. Most inhabitants could speak descendants of it shaped by the vessel's geography, professions, and social divisions. Different habitats might develop dialects or entirely separate languages. A message from Earth would require translation even if communication remained possible. The ship and solar system would have evolved independently. Each side could preserve launch-era language and still develop new ways of speaking. The name of the destination might change many times before arrival. Its original designation could become a sacred term whose pronunciation drifted. The arrival generation might step onto a planet carrying a name no launch engineer would recognize. Religion and mythology would also change with the number of generations. A 40-year mission might preserve beliefs close to those held at departure. A 400-year voyage could produce new traditions centered upon the ship, the destination star, and the obligations of ancestors. The founders might become revered figures. Their biographies could simplify into moral stories. Maintenance rituals could gain spiritual meaning because every life depended upon care for systems inherited from the dead. Air, water, and artificial soil might be treated as sacred substances circulating through generations. A long voyage could also produce movements rejecting the destination. Some groups might believe the ship itself fulfilled humanity's purpose. Others could insist that arrival represented a covenant no generation had the right to abandon. The number of generations increases the distance between original intention and living belief. A mission planned as a scientific project could become a religious pilgrimage, a hereditary obligation, or an ancient journey continued without faith. Arrival could create a profound crisis. A civilization organized around traveling may lose its central identity when the voyage ends. The planet chosen by distant ancestors would force the passengers to decide which parts of their shipborne culture could survive beneath another sky. Political stability would face different demands according to duration. 2 generations could operate under a mission command established before departure. 17 generations would need a constitutional society capable of transferring authority, resolving disputes, and revising law. A system designed to remain unchanged for centuries would become rigid. A system allowing rapid change could abandon safety standards or mission goals. The ship needs institutions able to distinguish fundamental physical constraints from inherited political preferences. Life support creates areas where ordinary choice is limited. The population cannot vote to stop maintaining the atmosphere. It can decide how labor is distributed, who supervises engineers, how data is shared, and what rights remain protected during emergencies. Long voyages create opportunities for temporary emergency authority to become permanent. A reactor failure could produce a technical government lasting several generations. A demographic crisis could lead to reproductive control that survives after the population recovers. Every additional generation gives political mistakes more time to deepen. It also gives the society opportunities for reform, learning, and cultural renewal. The mission's survival would depend upon institutions capable of recovering from periods of fear and concentrated power. The children born aboard would eventually ask why the ship continued toward the selected star. For the founders, the answer might be obvious. The destination offered the best-known planet. Earth faced danger, or humanity sought a second home. Centuries later, those reasons could feel distant. The vessel might detect a better destination after launch. New observations could reveal that the chosen planet had lost its atmosphere, or that another star contained a safer world. Changing course would depend upon fuel, current velocity, and the geometry of the available systems. A slow ship traveling for thousands of years could pass relatively near several stars. Its inhabitants might decide to settle one encountered earlier than planned. The original destination could become a symbol rather than an obligation. A faster vessel would have less time for political change and fewer opportunities to divert. Its speed creates a narrow trajectory. The two-generation mission preserves the founder's authority, partly because the voyage ends before descendants can transform the purpose deeply. The number of generations measures how many times the mission can be reconsidered. A journey lasting 17 generations is a chain of inherited decisions. A journey lasting 3,000 becomes an open-ended migration whose final planet may bear little relationship to the founder's map. Communication with Earth would influence cultural continuity. Proxima Centauri lies more than 4 light-years away, so messages near arrival would take over 4 years in each direction. A question and answer would require almost a decade. During the early voyage, the delay would grow gradually as the ship moved outward. A 40-year mission could maintain contact through delayed correspondence. Families would exchange messages, scientific institutions would provide updates, and Earth could follow the vessel's progress. The people at arrival would know that the latest news from home described a world several years in the past. A 400-year mission would receive messages from changing civilizations. The people who launched the ship would die, followed by their children and distant descendants. Earth might continue supporting the mission through institutions that reinvented themselves many times. Across 75,000 years, expecting continuous communication becomes difficult. Humanity on Earth could evolve, spread, decline, or disappear. The ship might receive silence for millennia. A later signal could come from beings who regarded both the founders and passengers as ancient relatives. Communication can preserve knowledge while revealing separation. Every message arrives after the sender has continued into an inaccessible future. A strange possibility appears when technology advances faster than the original ship. A generation vessel could leave Earth at 1% of light speed and expect a 425-year journey. 2 centuries later, humanity might develop a ship capable of 10% of light speed. The later vessel could overtake the first and reach Proxima centuries earlier. Its passengers might establish cities before the original generation ship arrived. The destination chosen as an empty frontier could already contain a civilization descended from people who left long after the founders. Earth could transmit news of the new technology. The generation ship would face a choice. It might continue, knowing arrival no longer carried historical priority. It could ask the faster civilization for assistance, change course, or attempt to upgrade using designs transmitted across space. The social consequences would be severe. Generations had accepted confinement because their mission represented humanity's first crossing. A later ship could complete the journey within one lifetime, turning centuries of sacrifice into a path rendered obsolete by progress elsewhere. This overtaking problem becomes likely for sufficiently slow missions. Launching before propulsion technology matures can lead to later travelers arriving first. The safest schedule for departure may involve waiting, although every period of waiting could produce another reason to delay. The possibility of being overtaken would influence mission design. The ship could carry modular engines and manufacturing systems capable of adopting future propulsion concepts. Earth might transmit new designs, though building them aboard would require suitable materials and industrial precision. A later vessel could rendezvous with the generation ship, transfer equipment, passengers, or fuel, and shorten the remaining journey. Matching velocity across interstellar space would be difficult and energy-intensive. The faster mission might pass nearby for only a brief encounter. Some passengers could choose transfer, abandoning the world where generations had lived. Others might remain because the old ship contained family, culture, and identity. A society could divide between those willing to accelerate toward arrival and those preferring continuity. The oldest generation vessel might become a traveling historical community, continuing after faster humanity spread among the stars. Its original purpose would evolve into preservation of a unique civilization born during the slow crossing. Technological progress could reduce the number of remaining generations while increasing social conflict within the present one. Distance to the selected planet can multiply every estimate. At 1% of light speed, Proxima Centauri requires around 425 years. Barnard's star would require approximately 600. Tau Ceti would require close to 1200. TRAPPIST-1 would require around 4000. Using a 25-year generation, these destinations correspond roughly to 17, 24, 48, and 160 generations. Acceleration and deceleration would add further time. A ship reaching 5% of light speed could divide those numbers by 5, bringing Tau Ceti within 3 or 4 generations, and TRAPPIST-1 within more than 30. The planetary choice therefore dominates the human chain. A world 40 light-years away may appear far more promising than one around Proxima. Reaching it at 1% of light speed would require a civilization older than the Roman Empire to be born and maintained entirely aboard. The first interstellar missions would probably favor nearby systems, even when their planets appeared less ideal. A difficult world reached within several generations may offer a better survival probability than a beautiful world requiring hundreds. Astronomy selects candidates by habitability. Interstellar engineering must also select them by the amount of history required to arrive. A target can become less attractive while the ship travels. The planet observed at departure belongs to the past because its light needed years to reach Earth. During a multi-century voyage, the destination continues experiencing climate, stellar activity, impacts, and geological change. A mission to Proxima receives relatively recent information by astronomical standards. A world around TRAPPIST-1 is seen 40 years in the past. The generation ship would continue observing it during the approach, gradually reducing the delay. A dangerous change might become visible only after the vessel had committed much of its fuel and history to the route. The longer the journey, the more time the destination has to change. The ship could arrive at a planet whose atmosphere no longer matches launch-era data. Native life could emerge, decline, or reveal hazards impossible to detect remotely. Every generation would update the settlement plan. The founders might imagine open-air cities. Later scientists could prepare sealed habitats. The final generation may discover that the planet offers no safe surface and choose an orbital colony. The number of generations measures the number of times the destination can be reinterpreted before anyone touches it. A 2-generation mission would raise questions about children born during transit. Their parents selected the journey and may have volunteered fully. The children inherit decades of confinement and arrive at a planet they did not choose. Their education would focus on settlement. They might spend childhood under artificial gravity designed to prepare their bodies. Every profession would be linked to arrival: medicine, construction, agriculture, ecology, geology, and atmospheric science. The parents would remain available to explain the decision. This could create trust or resentment. The child could ask why their life began inside a vessel and receive an answer from the person responsible. On a 17-generation mission, accountability becomes diffuse. The people living aboard neither selected the destination nor met anyone who did. The original decision survives through records and momentum. Descendants can challenge it politically while facing the immense energy required to turn. A 3,000-generation mission transforms consent into a foundational problem. Nearly every inhabitant lives within a world created by incomprehensibly distant ancestors. The ship must offer enough freedom and meaning that continuation remains a choice supported by the living. The emotional meaning of arrival changes with each scale. For the original crew of a 40-year mission, arrival completes a difficult project begun during their own lives. They can compare the destination with Earth and remember the people who watched them leave. For the fourth generation of an 85-year mission, Arrival fulfills the work of grandparents whose voices remain in family memory. The planet has shaped childhood directly, and preparation has occupied the society for decades. For the 17th generation, Arrival concludes a historical age. Every institution aboard has developed during transit. The ship contains cities, graves, traditions, and ecosystems older than anyone's understanding of ordinary travel. For the 3000th generation, stopping could feel more disruptive than continuing. The destination planet might be less familiar than the vessel. Its open landscapes, gravity, weather, and microorganisms would threaten bodies and cultures adapted to the ship. The longer the journey, the less Arrival resembles a return to normal life. It becomes contact between a moving civilization and a world selected by another form of humanity. Relativity changes the time experienced aboard when the ship approaches the speed of light. At 10 or 20% of light speed, the effect remains present and relatively modest. At velocities far closer to the limit, time dilation can become dramatic. A ship traveling at 90% of light speed would cross 4.25 light-years in under 5 years, according to observers near Earth, before acceleration and deceleration. The passengers would experience a shorter interval. At even greater speeds, they could cross much larger distances within one lifetime while decades or centuries passed outside. Reaching those velocities demands enormous energy. The vessel's kinetic energy would make every collision dangerous. Interstellar atoms would strike as intense radiation. The ship must slow at the destination, doubling much of the propulsion challenge. Relativistic travel can reduce the number of generations aboard without reducing the historical separation from Earth completely. A crew could reach a distant system after experiencing several years and discover that far more time had passed for the civilization left behind. The travelers would cross space and move into the future of everyone else. A mission avoiding generational succession could still lose its original era. Fusion propulsion offers one of the most frequently imagined paths toward a few percent of light speed. Fusion releases energy by combining light atomic nuclei, using reactions related to those powering stars. Controlled fusion for terrestrial power remains technologically demanding, and an interstellar engine would require performance, reliability, and fuel efficiency far beyond a stationary reactor. A fusion vessel might expel charged particles at extremely high velocity. Designs could use pulses or continuous thrust. The ship would need to manage heat, radiation, magnetic fields, and the manufacture or storage of fuel. If fusion enabled 5% of light speed, the nearest star voyage would enter the range of 3 or 4 generations. At 1%, it would require around 17. These two outcomes create profoundly different societies, even though both rely upon a similar broad energy source. Propulsion performance would influence the size of the ship. A system capable of accelerating a small scientific craft may be unable to move a habitat containing thousands. Reducing population lowers mass and increases genetic and social risk. Increasing population improves resilience and lengthens the acceleration period. The number of generations cannot be separated from the number of passengers the engine can carry. Antimatter could provide greater energy density because matter and antimatter convert mass into other forms of energy when they meet. The concept suggests propulsion capable of reaching substantial fractions of light speed. Humanity currently produces only minute amounts, and storing them safely remains extraordinarily difficult. A generation ship would need quantities created, transported, and contained with near-perfect reliability. Any contact between antimatter fuel and ordinary material releases energy immediately. Magnetic systems would have to hold the fuel through vibration, acceleration, radiation, and centuries of operation. An antimatter-catalyzed engine could use smaller amounts to trigger other reactions. Even then, the complete technology lies far beyond present capability. Heat management and shielding remain severe. If an antimatter vessel reached 10% of light speed, 2 human generations could reach Proxima. At 1 or 2%, the journey would contain around 8 to 17. The fuel technology could therefore determine whether humanity sends a crew with children or establishes a self-sustaining civilization. The shortest voyages demand the most dangerous concentration of energy ever placed near human beings. The long-generation ship avoids that concentration and accepts danger distributed across centuries. External propulsion could reduce the fuel carried aboard. A laser or particle beam built near the sun could push a sail over a long distance. The ship would gain velocity from infrastructure left behind, freeing it from part of the rocket equation. A crewed sail would need an immense area and extremely low mass relative to the force applied. It would also need protection, living space, and structural strength. The beam must remain aligned across millions or billions of kilometers. A small pointing error could move the energy away from the sail or damage part of it. Deceleration remains difficult. A magnetic sail might interact with the destination star's wind or the interstellar medium. Another beam could be built in the target system after an earlier mission. The ship might carry conventional fuel for slowing increasing mass again. Beam propulsion seems especially suited to probes. It could send information ahead, survey the planet, and report conditions before a slower generation ship arrived. These probes could reduce uncertainty without carrying people. The number of human generations might remain high while the mission's knowledge travels much faster. Robotic precursors could leave decades before the generation ship or accelerate past it later. A probe traveling at 20% of light speed could reach Proxima in just over 20 years, inspect the system during a rapid flyby, and transmit data toward Earth and the approaching vessel. The report would take more than 4 years to cross the remaining interstellar distance. If the generation ship traveled at 1% of light speed, it could receive detailed information centuries before arrival. The population would have time to alter habitats, landing equipment, crops, and medical preparation. A probe unable to slow would observe the system briefly. More advanced machines could decelerate, enter orbit, and build infrastructure. They might construct habitats, collect fuel, or establish communication beacons before human arrival. The first biological passengers could therefore belong to the 17th generation, while their robotic civilization had occupied the destination for centuries. Arrival would resemble reunion with machines descended from launch-era technology. The count of human generations would tell only part of the story. Mechanical agents could cross the distance faster and prepare a future no human had yet seen. A slow ship might use the interstellar medium for gradual deceleration or propulsion. Magnetic sails could interact with charged particles. Concepts such as ramjets imagine collecting hydrogen from space, although the medium is extremely thin and the practical challenges are severe. Every approach depends upon the density and behavior of material along the route. Interstellar space contains gas, plasma, dust, magnetic fields, and cosmic radiation. It is empty compared with planetary environments and sufficiently populated to threaten a fast vessel. At 1% of light speed, shielding must absorb repeated high-energy impacts across more than 4 centuries. At 10%, each impact becomes far more violent while the exposure duration falls. The optimal speed would balance travel time, energy, shielding, and system reliability. A faster ship reduces human generations and increases the punishment delivered by the space ahead. A slower ship gives shielding an easier task per collision and exposes the vessel across a much longer period. The safest speed may emerge from the total probability of failure rather than the engine's maximum performance. Generation counting also depends upon when births begin. A vessel could launch with young adults and delay childbirth until systems stabilized. This would reduce the number of generations present during the crossing while creating demographic risk if fertility declined or an accident affected the founders. Another design could include families and children from departure, establishing a natural age structure immediately. The first ship-borne generation would arrive earlier in the mission. Schools, childcare, and reproductive medicine would increase mass and complexity from the beginning. At 5% of light speed, founders could postpone births for a decade and still raise children who reached Proxima as adults. At 1%, delay changes little about the total of 17 generations and can create a dangerous gap between age groups. Long missions need a steady demographic rhythm. Children must be born early enough to replace specialists and late enough to keep population within the ship's capacity. Birth schedules could change the count by several generations without altering travel time. The human chain would be planned through bodies, relationships, and private decisions whose consequences extended centuries ahead. The meaning of a generation could become political aboard. The founders would form the first recognized cohort. The crossing generation might refer to everyone born before the midpoint. The arrival generation could include children expected to reach the planet. These names create identity and expectation. A person born shortly before a formal boundary might reject being grouped with older citizens. Another could feel deprived because arrival was expected just after their natural lifespan. Historical events would define generations more strongly than equal intervals. A reactor crisis, epidemic, civil reform, or habitat expansion could shape childhood for one cohort. Their attitudes would follow them into leadership. A 17-generation mission might be remembered through 5 or 6 broad cultural ages. A 3,000-generation voyage would contain histories, collapses, renaissances, and periods whose records disappeared. The numerical answer gives a clean chain. Human memory divides the crossing according to what happened within it. A 1% mission toward Proxima offers a useful central scenario. Around 17 25-year generations would pass during 425 years of ideal cruising. The real voyage could require closer to 18 or 20 after acceleration and deceleration. The first 2 generations would establish shipborne society. The 3rd through 6th might experience the vessel's early maturity when launch equipment began requiring major replacement. Later generations would inherit a ship rebuilt largely from local manufacturing. Around the midpoint, Earth would lie more than 2 light-years behind. Communication cycles would span several years. The destination would begin providing improved observations. Political debate over landing and route changes would intensify. The final 3 or 4 generations would prepare for arrival. They would adjust artificial gravity, develop crops for the target star, build landing craft, and study detailed data from precursor probes. Children born near the end could become the first settlers. This scenario remains immensely difficult and retains a human scale. Each generation could know people whose lives linked it with a meaningful portion of the voyage. The entire crossing could survive within records, institutions, and overlapping family memory. A 5% mission produces another central scenario. The trip lasts around 85 years before additional maneuvering time. 3 or 4 generations would be involved with substantial overlap. The founders would perform most of the early maintenance and could remain alive near arrival. Their children would become the principal working population during the crossing. Grandchildren born aboard could train for settlement and reach the planet as young adults. This structure preserves accountability and direct memory. The people who chose the planet would encounter its reality. The generation born into the mission would have access to the founders and could influence the arrival plan. The ship would still require a closed ecosystem capable of operating for a century. It would need reproductive medicine, schools, manufacturing, and replacement systems. Its society could resemble a remote colony or traveling city rather than a self-contained civilization extending through deep history. 5% of light speed may represent the threshold where a generation ship becomes comprehensible through ordinary family relationships. Achieving and surviving that velocity remains an extraordinary technical ambition. A speed of 0.1% creates the opposite scenario. Around 170 generations would pass on the way to Proxima. The ship's history would extend more than 4,000 years. The founders' names could survive through monuments and ceremonies while their language became ancient. The mission's charter would be revised repeatedly. Political orders could collapse and return. The population might divide among habitats with separate cultures and later reunify. The vessel would be rebuilt many times. Certain technologies could disappear and be rediscovered. Biological adaptation to artificial gravity, radiation, diet, and the closed ecosystem might become visible. The people reaching the destination could differ physically from the launch population. The journey would contain enough time for the ship to forget its purpose. Preserving navigation and destination data would remain easier than preserving emotional commitment. The vessel might continue through automatic systems after its inhabitants no longer believed strongly in arrival. 170 generations can carry humanity to another star. They can also create a new civilization whose relationship with the original mission becomes impossible to predict. At Voyager-like speed, 3,000 generations exceed the limits of ordinary planning. The ship would need to survive 75 millennia. Homo sapiens itself has changed culturally beyond recognition across comparable periods. Biological evolution could become significant. Genetic drift, mutation, selection, and deliberate engineering might transform the population. The descendants could become adapted to artificial gravity, controlled light, recycled food, and the vessel's microbial environment. Planetary life might require bodies they no longer possessed. The destination star would remain visually distant for nearly the entire history. A society could live through hundreds of cycles of expansion, decline, and renewal while covering only a fraction of the route. The ship might encounter changes in interstellar conditions, navigation, and cosmic events impossible to forecast. An object built to last 75,000 years would need continuous self-reconstruction. The population itself might become distributed among multiple vessels produced during the voyage. A single-generation ship could evolve into a fleet or a moving network of habitats. At this duration, humanity would reach another star through migration and evolution, rather than one mission in the familiar sense. The arrival generation would inherit the greatest transition. Every previous cohort lived inside a closed world with a stable purpose. Continue traveling. The final population must slow the ship, evaluate the planet, and decide where humanity lives next. Their bodies may have developed under artificial gravity. Their immune systems may be adapted to the ship's microbes. Their culture may treat walls, monitored air, and recycled water as natural conditions. The planet would introduce weather, geology, native chemistry, and open distance. Landing could occur gradually. Robots would survey first, small crews would enter sealed habitats. Children might adapt more easily than adults. Some citizens would remain aboard permanently. The number of generations affects how foreign the planet feels. A child of the founders may consider it a destination. A member of the 17th generation may consider it an unexplored environment connected to ancestral duty. A member of the 3000th could see it as an alien world threatening the only civilization humanity remembers. Arrival concludes distance and begins a negotiation between two environments. The ship itself could become too valuable to abandon. After centuries of life, it would contain cities, ecosystems, archives, industries, and memorials. The destination planet might require terraforming or sealed settlements. Remaining aboard could offer greater safety. The society might enter orbit, collect local resources, and build additional habitats. The planet selected by the founders would serve as a scientific site, material source, or future option. Human civilization would have reached another star without ending its life between walls. A 3-generation mission would probably retain a strong desire for planetary settlement. The founders remembered Earth and built the vessel as transportation. A 17-generation mission would possess a deeper shipborne identity. A 3,000-generation population might consider planetary settlement a radical cultural experiment. The number of lives during transit shapes the meaning of the destination. Every generation adds memory to the vessel and removes direct memory from planets. The longer humanity spends between stars, the more likely the ship itself becomes the world its passengers were seeking. There may be no single first-generation ship. Humanity could send many vessels at different speeds toward several stars. Some would carry families, others would carry embryos, sleeping passengers, digital minds, or robotic factories. A fast probe could reach Proxima within decades. A fusion ship might arrive within a century. A slower city could continue for 400 years. Their populations would embody different answers to the same distance. The faster missions might establish infrastructure and receive the slower vessels later. The slow ships could preserve cultures that disappeared in the solar system. Each arrival would add another historical branch of humanity to the destination. Generations would also continue on Earth. During a 425-year voyage, 14 to 17 generations would be born at home as well. The civilization welcoming messages from the ship would differ greatly from the one that launched it. Interstellar travel multiplies humanity across time. The travelers, the people left behind, and later missions all move through separate histories connected by delayed communication. The simplest answer can be stated through several scales. With present probe velocities, reaching Proxima Centauri would require around 75,000 years and approximately 2,500 to 3,000 generations. Sustaining the peak speed reached by Parker's solar probe would reduce the journey to more than 6,000 years and roughly 200 generations. At 1/10% of light speed, the crossing would take about 4,250 years, producing around 140 to 170 generations. At 1%, it would take about 425 years and require around 14 to 17. At 5%, approximately 85 years would involve 3 or 4 generations. At 10%, roughly 42 years could be completed by one aging launch generation and the children born during transit. At 20% of light speed, the ideal travel time falls near 21 years. Such a speed has been proposed for tiny laser-driven probes rather than inhabited vessels. A crewed ship would need to accelerate and decelerate an incomparably larger mass. Every estimate grows when the destination lies beyond Proxima, and each depends upon the full trajectory rather than cruising speed alone. The useful answer may therefore be 17 generations. 1% of light speed remains extraordinarily ambitious while lying closer to imaginable future engineering than a crewed vessel traveling at 10 or 20%. A 425-year journey is long enough to require a complete generation ship and short enough to preserve a continuous civilization through deliberate effort. 17 generations could know the same broad mission, read the same archives, and maintain institutions descended visibly from the founders. They could rebuild the ship several times without crossing geological ages. Genetic diversity could be protected through a sufficiently large population and stored reproductive material. The number still carries immense uncertainty. A century of additional acceleration and deceleration could add several generations. Equipment failures, route changes, or a decision to target a more distant star could double the crossing. Future propulsion could reduce it drastically. 17 generations is therefore a scenario rather than a prediction. It gives human scale to the distance. The first generation launches. The middle generations keep a world alive where no planet exists. The final generations prepare to meet a sun whose light guided every ancestor aboard. Imagine the ship during its 9th generation, near the midpoint of a 1% journey. Nobody alive has seen Earth directly. The destination remains more than 2 centuries ahead. The vessel's oldest habitats have undergone several reconstructions. A child learns that 8 generations lived before her and 8 may follow before arrival. She occupies the center of a human chain whose ends remain unreachable. The founders belong to history. The settlers belong to imagination. Her life still contains immediate purposes. She studies engineering, cares for a garden, forms friendships, and repairs systems that will serve children she may meet. The mission becomes real through the people around her rather than the distant planet. This middle generation may carry the greatest burden. It receives little glory from departure and expects none from arrival. Its work preserves continuity because ordinary responsibility remains valuable even when history offers no visible reward. The success of the entire voyage depends upon generations willing to live fully in the middle. The final child born before arrival would inherit another world of expectations. Every school lesson would prepare for a planet. Artificial gravity might be adjusted toward surface conditions. The destination star would shine brighter than it had for any earlier generation. The child could meet elderly people born when the planet remained a point visible only through instruments. Family stories would stretch toward the midpoint. Archives would extend to Earth. During adulthood, the ship would begin slowing. Planets would become visible as worlds. Robotic reports would replace old astronomical guesses. The child would discover whether the home selected by 17 generations of ancestors contained oceans, air, life, or danger. Their first step would represent thousands of births, repairs, arguments, sacrifices, and ordinary mornings inside the vessel. Arrival would belong to the living and carry the weight of the dead. Perhaps the planet would prove unsuitable. The atmosphere could be toxic, the climate unstable, or native life vulnerable to contamination. The arrival generation might remain aboard, settle a moon, or redirect the ship toward another star. The voyage would continue beyond the number calculated at launch. 17 generations could become 30, 50, or more. Children born during the second crossing would inherit a mission altered by the failure of the first destination. This possibility reveals the deepest uncertainty in counting generations. Distance and speed can be calculated. Success cannot. The ship may travel for centuries and discover that arrival requires another journey. A civilization capable of surviving 17 generations between stars must be prepared to continue when the chosen world refuses them. Its true destination may be any place where humanity can build a stable future, including the vessel itself. How many generations would it take to reach another star? With the machines already moving beyond the solar system, the answer lies in the thousands. With propulsion reaching 0.1% of light speed, the answer lies in the hundreds. At 1%, it falls near 17. At 5%, a family could span the entire crossing. At 10%, children born after departure could land beside the parents who began the journey. The numbers describe engineering and also describe the distance between human worlds. 3 generations preserve family memory. 17 create a civilization. Hundreds allow culture and biology to transform. Thousands turn the voyage into an evolutionary migration. No engine carries people through space alone. It carries language, childhood, government, grief, reproduction, knowledge, and the obligation to maintain a future beyond one life. Every reduction in travel time removes generations from that responsibility and adds demands upon energy and protection. The first humans to reach another star may arrive after 20 years, 4 centuries, or several thousand. Their ship will reveal which problem humanity learned to solve first: the speed of the vessel or the endurance of the people inside it. The destination waits only in distance. The generations must carry one another across the time.